In this lecture, first we shall study Archimedes' principle. Fluids exert upward buoyant forces on objects in the fluid. These buoyant forces either completely or partially support the object's weight. For example, the buoyant of water supports a person's weight while floating in a swimming pool. The buoyant force of seawater supports the million-pound weight of iceberg. The atmosphere exerts a buoyant force that helps support the weight of a balloon. To derive an equation for calculating the buoyant force of a fluid on an object, let us consider a metal block immersed in a liquid as shown in the figure that I am now drawing. This is the surface of the fluid. Here, for simplicity, we can consider it is a liquid. And the fluid will apply, they will exert pressure, force on all the surfaces of the material that is inside the fluid. The fluid exerts forces on all the 6 surfaces of the block. Okay, this is the metal block. The forces exerted on opposite sides of the block cancel each other, so these forces will be cancelled with these forces because the heights are same from the surface of the fluid. However, the upward force F1, let us say F1, this upward force on the block due to the fluid pressure from below, and the downward force F2 due to that from above the block do not cancel. This is F2. This is the downward force on the upper surface of the metal block, and there will be a resultant force of these F1 and F2. But since the lower surface of the metal block, the depth of this surface is greater than the depth of the upper surface of the metal block, so the force due to the pressure on the lower surface of the metal block will be greater than the force due to the pressure on the upper surface of the metal block. The net fluid force is called the buoyant force, and we will denote it by FB, and which is F1 minus F2. It will point upward, and if the area of cross section of the upper surface or lower surface of the block is capital A, and if the pressure on the lower surface of the block is P1 and the pressure on the upper surface of the block is P2, then we'll have here P1A minus P2A. The area of the upper surface is equal to the area of the lower surface. If we take common, this force is known as the buoyant force, of the fluid, and this is the magnitude of that force. The difference in pressure at two different elevations in the fluid is given by, we know this one from a previous lecture, that the difference in pressures, and which is equal to rho g, and the difference in the depths of the upper surface and lower surface. And if we substitute this into equation, let us say this is equation 1 and this is equation 2. So if we substitute 2 into 1, and then we can write down the buoyant force as rho g y2 minus y1 into a. But this product is the height of the block and the area of cross section, so it is the volume of the block. So rho g, and this is volume. Let us say this is equation 3, where v is y2 minus y1 into e. Now it is important to note that the density rho, this rho is the density, and it is for the fluid, the density of the fluid, and v is the volume of the block. So we can say that this rho into v, this is the mass of the displaced fluid. Then we can then say that the buoyant force is nothing but the resultant upward force due to the pressure difference between the upper surface and the lower surface of the block in the fluid. The buoyant force Fb exerted by a fluid on the object in the fluid is equal in magnitude to the weight of fluid displaced by the object. Any object totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the fluid displaced by the object. Archimedes' principle allows the buoyancy of any floating object partially or fully immersed in a fluid to be calculated. The downward force on the object is simply its weight. The upward or buoyant force on the object is that stated by Archimedes' principle above. Thus, the net force on the object is the difference between the magnitudes of the buoyant force and its weight. Okay, the object that is inside the fluid we have shown here. Okay, this body will sink or it will float inside the liquid, or it will rises to the surface, will depend on the difference between the weight of the object and the buoyant force. If this difference, if we say the buoyant force Fb and let us say W is the weight of the uh, object, and if this difference is greater than 0, this is the weight of the object, or the block we have shown, and this is the buoyant force of the fluid on the object. And if this difference is greater than 0, then the object will rise. This is 1. Now, 2, if this Fb minus W is negative, then the object sinks. And third, if the buoyant force is equal to the weight of the object, then that means the difference is 0. We can write down this minus W is 0. Then the object will be neutrally buoyant. that is, it remains in place without either rising or sinking. In simple words, Archimedes' principle states that when a body is partially or completely immersed in a fluid, it experiences an apparent loss in weight that is equal to the weight of the fluid displaced by the immersed part of the body or object. Okay, let us now discuss about the phenomenon of surface tension, and we shall first discuss the molecular theory of surface tension. To discuss surface tension, let us first discuss about the cohesion and surface tension, cohesive force and adhesive force. The force of attraction between molecules of same substance is called cohesive force. And adhesive force, the force of attraction between molecules of different substances. Okay, now we should study cohesion and surface tension. The cohesive forces between liquid molecules are responsible for the phenomenon of surface tension. The molecules at the surface do not have other like molecules on all sides of them, and consequently they cohere more strongly to those directly associated with them on the surface. This forms a surface film, which makes it more difficult to move an object through the surface than to move it when it is completely submerged. The cohesive forces between molecules down into a liquid are shared with all neighboring atoms. Those on the surface have no neighboring atoms above and exhibit stronger attractive forces upon their nearest neighbors on the surface. This enhancement of the intermolecular attractive forces at the surface is called surface tension. Now, how do we define mathematically this surface tension? The surface tension is defined as the force per unit length acting on both sides of an imaginary line drawn on the liquid surface at rest. The direction of the force is tangential to the surface and perpendicular to the line that is imagined. If a force F acts perpendicularly on both sides of a line of length small l drawn over a liquid surface, and if the force is tangential to the surface, then the surface tension would be T equal to force divided by length. So if you consider that we have a surface of a liquid here, and if you consider there is a straight line, there is a line, and some attractive forces acts on the molecules on the surface, and we consider these forces are perpendicular to the line, and if the length of this line is small n, and if the force due to surface tension is F, then the surface tension T is mathematically defined by this relation. The unit, this is surface tension, the surface tension is force per unit length, so the unit of surface tension is Newton per meter. Okay, Newton per meter. Now the surface tension of water, this is an example. Okay, surface tension of water is 72 into 10 to the power minus 3 Newton per meter. What is the meaning of this? This means that if we imagine a line of length 1 meter over the water surface, then a force of 72 into 10 to the power minus 3 Newton acts perpendicularly on both sides of the line and tangentially to the liquid surface. Now we discuss the molecular theory of surface tension. Surface tension is a molecular phenomenon and it can be explained by molecular theory. Laplace first explained surface tension with the help of molecular theory. Before presenting molecular explanation of surface tension, we must mention again the two types of intermolecular forces, attractive forces. We have already discussed this about the cohesive force and adhesive force. The maximum distance at which the cohesive force between two molecules remains active is called the range of molecular attraction. It is nearly 10 to the power minus 10 meter. So is range of molecular attraction. This is a natural phenomenon. The molecules of the same fluid, they attract each other. So the range of molecular attraction is nearly 10 to the power minus 10 meter. So you see, this is a molecular phenomenon. If a sphere is drawn with a molecule as its center, so if we consider a molecule here and we draw a sphere with radius, so if this is R, okay, then the molecules inside this sphere will be influenced, or this molecule will be attracted by all the molecules inside this sphere, and this sphere is known as influence sphere of the molecule, or range sphere of the molecule. Influence sphere. The molecule at the center, okay, this molecule is only influenced by the other molecule within this influence sphere, but not by the molecules outside this sphere. Okay, so these molecules will not attract these molecules. This means this molecule at the center of the influence sphere has no cohesive force with any molecules laying outside this sphere. Now if we draw another figure showing three molecules of a liquid, we consider the liquid here, and this is the surface. Okay, we consider a sphere of influence here, another sphere here, and another here. Okay, we call this A, and this is B, and this is C. Let us say this is PQ, this is the surface of the liquid, and this is RS. The molecule A is inside the liquid, hence its influence sphere of molecular attraction is inside the liquid. This molecule A is equally attracted in all directions by the molecules of the influence sphere. Thus the resultant cohesive force on it is zero. There is no cohesive force is acting on molecule A. Therefore the molecule will remain in the state in which it is situated. The molecule B is in such a position that a portion of its influence sphere is lying outside the liquid. The number of the molecules in the lower half of the influence sphere will be greater than the number of molecules in the upper half. Thus the downward cohesive force on molecule B will be greater than the upward cohesive force. Therefore the molecule B will experience a downward resultant cohesive force. Now we consider molecule C, which is situated at the free surface of the liquid. The upper half of the influence sphere of C is laying outside the liquid, and the lower half of the sphere is laying inside the liquid. Thus there is no cohesive force on the upper portion, only downward cohesive force is acting on the molecule. Therefore in this case, the molecule C will be attracted by the maximum downward cohesive force. Thus, among the three molecules situated at different positions, the tendency to go downward is maximum for the molecule C. Now, if we imagine a plane RS parallel to the surface, liquid surface PQ, and at a distance equal to the molecular range and inside the liquid, then all the molecules lying between PQ and RS will experience downward tension due to cohesive forces. The magnitude of this downward tension will increase with the distance from RS toward the free surface and will be maximum at the free surface. Now, to bring a molecule above the RS plane from a point inside the liquid, work must be done against the cohesive force, and this work will increase the potential energy of the molecule. Thus, the potential energy of the molecules above RS is greater than that of the molecules below RS. But we know that all objects tend to come to lowest potential energy configuration. To minimize the potential energies of all molecules lying between RS and PQ, the area of free surface must be diminished. Hence, the free surface of the liquid always tries to diminish its area and tries to contract. Thus, the free surface of the liquid acts like a stretched elastic membrane and remains stretched. This tension acts along a tangent to the surface. If we draw a line on the surface of the liquid, then this tension will be perpendicular to that line. The tension arises per unit length of this line is the surface tension. Okay, now we understand how the surface tension arises, and this is given by the molecular theory. Okay, this is for today. In the next lecture, we shall discuss about surface energy of the liquid and angle of contact if a solid comes to a liquid, and then we shall discuss about capillarity if a tube with very small radius is inside. If you put this inside a liquid, then liquid rises inside the tube. This is known as capillarity. And finally, we shall discuss about the determination of surface tension of a liquid.